Okay, good evening everybody. Hope all of you are doing really well. I guess it's kind of the end of half term, so I'm sure a lot of you have that kind of sinking feeling about going back to school tomorrow. Now, I'm not sure if this stream is going to work because the office I'm in, there's been some internet issues. For some reason, yesterday it was absolutely fine. I did like a 3.5 hour AQA paper 2 live stream for A-level. I can see that obviously the stream is working. There's people in the chat. So hello, Joe, and other people joining just now. So it's brilliant to hear that some people are there. But yeah, I'm not sure how this stream is going to go in terms of like upload speed. I think it's the upload speed is okay, but the download speed is really slow. So if there's any issues, then anything I can't do tonight, I will do tomorrow instead. So I might do like a longer A-level thing. Failed Organ says that you're bricking it for A-level on Thursday. Yeah, completely understandably. I think a lot of people who did OCRA had quite a hard paper and are probably expecting a hard paper for paper 2, but you never know what's going to happen. I'm sure paper 2 is going to be fine. So I think it's completely understandable to be, nervous and apprehensive about the exam, but fingers crossed everything works. Yeah, so Bramble asking about mass defect and binding energy. I did do some stuff on that in the streams over the last couple of days. So depending which exam board you're doing, what you can do is just go back to YouTube. You'll see on my main page at Physics Online, there should be a section where you can see all the live streams that I've done. And it might be if you find either OCR, AQA or EdXL, you can just skip forward in the live stream because I kind of tend to do it in spec order, and I do talk a little bit more about mass defect and binding energy. Of course, if there's anything that anybody needs for A-level in particular, or even GCSE, that maybe hasn't been covered in one of my lives, I do have pre-recorded videos about anything in GCSE and A-level physics, or pretty much anything, and you can go back there and find just the stuff that you need. Right, I'm going to go on to A-level at 8 o'clock. That's the plan if the internet keeps working. Do we have any GCSE people in the chat? Do let me know if you are there. I know a lot of you have maths exams tomorrow. You've got paper 2, which again, don't forget your calculator for. Make sure that you've always got a protractor, ruler, all that kind of good stuff. So yeah, I know a lot of you GCSE folk are going to be preparing for maths tomorrow. But of course, it's maybe a couple of weeks away until paper 2. And all the stuff I'm doing tonight is really based on the kind of topics that come up in paper 2, especially for AQA. So the first one, we've got a question. The scenario is really about mountain bikes, or I guess this is more like a road bike, I suspect. But the first bit is very much a simple definition. Of course, if you're A-level, you're more than welcome to join in and watch this and reminisce about GCSE. Yeah, this drawing here took me a while. Thank you, the slow-mo. All done on PowerPoint, basically just by grouping objects. Some of the ones like down here, it's a little bit more difficult to draw, but I tried to simplify this as much as possible while still keeping it accurate in terms of what bikes look like. So we've just got like a single fixed gear here, got some cranks, and yeah, basically a very simple diagram of something. And here we have a roller at the back. But the first part, basically we just need to define what is meant by the moment of a force about a given point. So this one over here then, the moment of a force is basically the turning effect of a force and it's a turning effect of a force about a pivot. Okay, now at GCSE we tend to have like some kind of fixed pivot or a hinge, and we tend to maybe think about at a certain distance, maybe this is the pivot over here, and we often just use this triangle to sort of represent that. There might be a force applied at this point over here, and that's a certain distance away. Now the distance could be given the letter S or X or D, and basically the bigger the distance to that force, the bigger the turning effect, because the moment is equal to the force times the perpendicular distance to that pivot. Okay, and of course a lot of stuff about moments is, and I think Slow-Mo sort of said this in the comments as well, that basically you can find them everywhere. It explains a lot of kind of everyday life. It explains why tools are designed the way they are, and like lots of everyday features like door handles. There are so many things when you look around you. But also as you go into A-level, you realise that you can actually use moments to solve things which aren't even rotating, and you can basically look at systems in equilibrium and how you might have no resultant force and no resultant moment on those systems. Okay, now the next bit is the kind of questions which kind of do throw people sometimes at GCSE. There's a lot of wordy stuff and there's lots and lots of information. Now some of that's going to be useful, some of it is a bit of like a red herring. It's not necessarily that important. So we've got the rear wheel of a bike, and basically this is pressed against a small wheel on a stationary trainer. Okay, so as this person pedals, so there might be a force applied here at a certain distance away from the pivot. That's going to cause the chain to rotate, which is attached to the small cog at the back, and that means this wheel is going to rotate like that. So if this is rotating that way, then at this point down here, that's going to be going that way, and this wheel is going to be in the other direction. And this wheel basically provides some friction, and it kind of holds the bike in position, so you can basically keep pedaling like with a Peloton bike or something like that. And in this case, it's pedal to the back wheel maintains a constant rate of rotation. So it's just going round at the same speed. Now, we've got the radius of the bike wheel, including the tyre, is 32 centimetres. And sometimes if you have information like this, adding it to your diagram can be really useful. So this distance here is 32 centimetres. The radius of the small wheel on the stationary trainer is 1.25. So that radius from here to here is equal to 1.25, and the radius of the cog driven by the bike chain in here is equal to 3.0 centimetres. Okay, now of course, if you do get something in centimetres, I think it's always really useful to maybe underline the unit and maybe think about how all of these distances here could be converted into metres. Now the next one, so there's lots of information there. What do we need to know? Well, it says the small wheel on the trainer exerts a force of 25 newtons. So that's a force here of 25 newtons parallel to the bike tyre, and this force is labelled A in figure 12. So again, you might be given numbers. It's always worth putting those onto your diagrams. Calculate the moment exerted on the bike tyre about the axle. So the moment on the bike tyre is going to be equal to the force here multiplied by the distance away, the perpendicular distance away. Okay, now the moment is equal to the force times that perpendicular distance, which is equal to the force of 25 newtons times the distance of the bike tyre away from the axle of the wheel, and that's equal to 32 centimetres, which is 0.32 of a metre. And if you multiply those together, we then get an answer equal to 8.0. Okay, you can just give it as 8, that's absolutely fine at GCSE, but what I've tended to do in these practice papers that I've put together, which you can buy in my shop, GCSE people, a huge amount of extra questions to help you over the next couple of weeks, but basically the moment is equal to 8 Newton meters, or 8.0 is a better way of presenting that, because we've got our force here in newtons, a distance in meters, and therefore our units are Newton meters when we look at moments. Okay, so that's the first bit, not too bad. Then it says a moment of equal magnitude is required to that calculated in part 9.2, so 8, to keep the rotation rate of the back wheel constant. The moment is provided by the force of the chain on the gear of the back wheel, parallel to the rotation of the gear. The force is labelled B in the figure. Okay, so there's going to be another force over here. So there's this force B acting at a distance of 3 centimetres away. Calculate the force applied by the chain to the gear. Now effectively, at this point here, we've got something in equilibrium, so it's not getting faster or slower, and therefore the moments are going to be balanced. So we could say that the clockwise moment is equal to the anti-clockwise moment. Okay, now effectively we've got, at this point, there's going to be a moment equal to 8.0 newtons, which is acting on the outside, and that must be equal to the moment provided by the force of the chain on the cog. Now that force is unknown, but we know the distance it's applied at is equal to 3 centimetres, because that's the distance for that cog. So it's 0.030 of a metre. And of course, I guess that means that the force is equal to 8.0 divided by 0.030, which is going to be the same as 80 over 0.3, or 800 over 3. 800 over 3 is equal to 266.66666. But of course, we want to give our final answer to an appropriate number of significant figures. I reckon 2 significant figures is good because that's the kind of how much we know the force is. So that's to 2 significant figures over here. And so I'm going to round that up to 2 significant figures as 270 newtons. Okay, you could, of course, if you wanted to, give it in standard form as 2.7 times 10 to the 2 newtons. That's also an appropriate answer. But again, I think at GCSE they're not too picky most of the time. So I would give an answer potentially of 267. All of these would get you the mark. What they want to see, though, is that you've equated the moments and used that to work out the size of the force. Okay, but of course, if you have a larger cog on the back wheel, at the same speed of rotation of the wheel, it would change the demands on the bike rider. So basically, if you had a bigger gear at the back, this is a bit like when you're on your bike and you change down to a lower gear, you find it's easier to pedal. So maybe this is what you use when you're going really fast down a hill, and then if you wanted to go uphill, you'd move the chain onto the bigger sprocket at the back. So explain why less force is needed to turn the gear and the chain must move faster in this scenario over here. Okay, so again, this question here, it's the kind of thing that I reckon most students would kind of intuitively know. And if you had a conversation with most people, you know, if we had like that one-on-one conversation, you'd have a good idea about how to answer this. The difficulty is when it comes to an exam, you see a big space and lots of marks. But a lot of the time, you gain lots of marks by stating obvious things. So you could say that over here, what we have is a force being applied by the chain. But here, that force is going to be applied at a much bigger distance from the axle. So we can say that the force applied is now further from the axis of rotation, or the pivot about which that force is applied. And that means, so a smaller force is needed to produce the same turning effect. So basically what we can do is apply a smaller force to get the same turning effect if you apply a force at a bigger distance. So you can have a smaller force. So effectively, you know, the moment is equal to the force times the distance. Here, we can have the same size moment by applying a smaller force at a much bigger distance. And smaller force times a bigger distance equals that same size moment. But of course, that means if we think about maybe one of the teeth, because there would be teeth on this which are rotating as well. So a smaller force, explaining why less force is needed to turn the gear. So we've kind of done that bit. And the chain must travel faster. Okay. So if you're applying a smaller force at a larger distance, you might apply a smaller force, but you might have to rotate your legs quicker. You know, this is the kind of thing, again, imagine you're riding along a flat piece of road. If you have a very small gear at the back, you only need to turn your legs quite slowly. But if you turn down to a lower gear, then that means you need to kind of spin your legs much quicker. And we could say that the tooth on the cog travels further in one rotation, because here it's kind of moving this distance. Here, that distance it moves is much bigger. So the tooth on the cog travels much further in one rotation as it travels a greater distance in the same time. It must be travelling quicker. And of course, if it's travelling quicker, then that means the chain must be travelling quicker as well. Okay, so that one there, just a nice straightforward question about moments. We now have a question about electromagnetic waves. Okay, so first of all, if anybody's watching this, including the A-level people who are desperately waiting for whatever happens at 8 o'clock, I know there's quite a few people watching at the moment, all of you can play along. State two properties shared by all electromagnetic waves, but not by all waves. Okay, so I think this question here, I think it's quite a nice question, to be honest. So I've just lost my chat. Okay, right, so what property is shared by all electromagnetic waves, but not necessarily by all waves? So this one here means you need to consider longitudinal transverse waves, sound waves, water waves, and things like that. So what is it that electromagnetic waves have in common, but not all waves have? So a couple of properties of electromagnetic waves is that they all travel, and all, I mean EM waves, that they all travel at the speed of light in a vacuum. So as they go through space where there's no air particles, or even in air, which is kind of almost a vacuum, they travel at the speed of light in a vacuum. Not all waves do that. Things like sound might travel at about 330 or 340 meters per second. They can be polarized. Excellent. And they oscillate perpendicular to the direction of energy transfer. James, they can travel in a vacuum. Perfect. Yeah, so they all travel at the speed of light in a vacuum, or they can they don't need a medium to travel through. So it's not necessarily a mechanical wave. So mechanical waves tend to use particles, things like air waves, things like seismic waves, like P and S waves. Bramble talks about that they can be polarized, which is like more an A-level thing. But of course, if you've done a bit of reading around the subject, if you've watched videos, if you've kind of started looking at A-level textbooks, and you put down an A-level answer, they should be able to give you the mark, because that's something that is a completely true physics fact. So yeah, there are lots and lots of things that electromagnetic waves have, but not necessarily all waves. Okay, we then have the table. I'm going to call this A, B, and C. What I'd like you to do is, if you want to in the chat, just maybe put your answer for A, your answer for B, and your answer for C. So we just need to complete the table with which part of the EM spectrum matches each property in the table. So for example, the first one is done for you. So detectable by the human eye, we've got visible light. Of course, we can't detect radio waves or microwaves. We can't detect infrared. We can't detect ultraviolet, gamma, or X-rays. So yeah, what do you reckon has the longest wavelength of all of the electromagnetic waves? What is produced by changes in atomic nuclei? That one there is quite a nice one. I do like that one. And what is produced by oscillations in electrical circuits? Spire says that Edexcel is definitely harder than AQA. Is this for GCSE or for A-level, Spire? I think each exam board basically assesses the same material. So in terms of the content taught, each exam board tends to, especially at GCSE, there's very little difference between OCR, Edexcel, and so on. And even at A-level, most of the content is the same, but sometimes some exam boards just set the questions just seem to be a little bit more tricky. But yeah, I think it depends on, so many different factors. Right, so the longest wavelength of all the electromagnetic waves is radio. So radio waves have the longest wavelength, and they have the lowest frequency. Right, the thing that's produced by changes in atomic nuclei is the thing that can only be emitted from the nuclei, so not necessarily as an electron jumps from one energy level to the other, but the thing that's actually produced in atomic nuclei is gamma. Okay, and that's why gamma is nuclear radiation. It's radiated from the nucleus of an atom, and it's basically when the nucleus is in a higher energy state, and as it drops down, it emits some gamma radiation. Okay, so that's one from a nuclei of that. And the one which is produced by oscillations in electrical circuits is again a radio wave. So radio waves tend to be produced if you have an aerial like this, and what you have inside the aerial is lots and lots of electrons. Now if you push the electrons up and then back down again, we have an alternating current, and as the electron here basically moves up and down, its electric field around it kind of radiates outwards like this. Okay, and as the electric field kind of radiates away, there's also then an associated magnetic field, which is at 90 degrees to it. Okay, and what we then have is an electric field and magnetic field kind of moving away at the speed of light, and that's what we call an electromagnetic wave. And of course we can then have another wire over here, and as this wave gets towards this, this electrical, this electric field which is changing causes the electrons inside it to move up and move down, and what we then can do is detect an alternating signal, and if we look at the frequency of that, we can then convert those radio waves back into electrical signals to play on an old style radio. Okay, right. The next one is about colour. Again, this is like very much a triple science kind of thing. So we've got something that basically these are the colours that things really are. So red, black, white and blue. And then if we illuminate it with red light, what will happen? So if you have a red object here, and you shine some red light onto it, what it will do is it will reflect that red light. Okay, so that's probably not the best diagram. However, if you shine some blue light onto it, this object will absorb the blue light and then it won't emit any other radiation because all the blue is absorbed by this colour, and that means it appears to be black. Okay, now if you have a black object, so this is our black object over here, and you shine red light onto it, red light is absorbed by the black object because black things are really good absorbers of radiation, so not just infrared but colour as well, and it's not going to reflect any colour back, so it appears to be, in red light, it appears to be black. Okay, it's quite useful having these, and of course, just likewise, if you shine blue light onto it, all the blue light is absorbed as well. If, however, you've got something which is white, if you shine red light onto it, because white is a poor absorber, it's going to reflect all of that red light, and that means it appears red. And if you shine blue light onto it, it reflects all of that light, and it appears to be blue. And finally, if you have your blue object over here, and you shine red light onto it, the blue object absorbs the red light, and therefore it looks black. And if you shine, of course, blue light onto a blue object, it's going to reflect that blue light and it appears blue. So there we go, even perfectly colour-coded. Right. John, you've got a good question there about multiple choice questions. I think your question is basically, is it better to do multiple choice questions for a set amount of time, or better to do them in like a chronological order? I reckon if it was me, I would start the paper with the multiple choice questions and I'd work through them really quickly and just do the easy ones first of all. The ones which I know the answer is kind of obvious, or it's just a kind of quick calculation. If there's a multiple choice question which takes lots and lots of reading, lots and lots of thinking, or quite an in-depth calculation, I just skip it and move on and do it at the end. So I would start a paper with the multiple choice ones, do the easy ones, get them out of the way, go on to the longer answer, normal questions, and then at the end, as I'm checking through the paper, go back to the multiple choice questions. That's just me, but the most important thing is not to spend too long actually on those questions. Right, Bramble, how long would I suggest on each section of the paper? I think it's really up to you. I wouldn't, to be honest, I'd try and work through the whole paper fairly quickly rather than trying to answer everything to completion. So yeah, I think it's, in terms of my approach to a paper, I'd work through it quite quickly. So if it was like, say for example, it was an hour-and-a-half paper, I'd try and do all of the questions, or like most of the questions in like the first kind of say 45 minutes. And if I know it's going to be difficult, I'll just come back to it later. And then as I come back to it, I've had probably a bit of time to think about some of the questions in my head. And then that means I can really kind of go to town on like the really more difficult ones, making sure that if it's too difficult, I'll just leave it to the end. Okay, you don't need to get 100%. If you're getting 80% in an exam, that's going to give you a grade 9 or an A star at A level. So you can get 20%, or you can even leave 20% and not even have a go at them and still get the top marks. So I think it's better to do a bit of everything than try and do the first few questions really well and then run out of time later on. Okay, Okay, John also says, thank you for the mock paper 3s for AQA A-level physics. They're a lifesaver. Yeah, thank you so much. Okay, right. Why can you not see your own reflection in a brick wall? Okay, so basically, this is kind of obvious stuff. So we can say that the brick is rough, or the surface of the brick is rough. So only diffuse, and this is a good kind of chance to get some good scientific language in there. So only diffuse reflections of light occur, and basically, and that means you cannot form an image or tell where the reflected rays come from. So what we mean by that is if you have a specular reflection, you basically get all the rays of light coming in, and everything that comes off is parallel, and that means your eyes kind of over here can tell where that comes from. If you have a rough surface like a brick like this, when rays of light come in, they don't all reflect out in the same direction, and that means you basically see lots of rays of light coming like this, and you can't necessarily tell where they come from. Okay, right. G Dominators official, been selected for the upcoming IFO camp. G, that is awesome work. I suspect there's not many people, and there's like a lot of competition, so congratulations. It's always, do let me know, and of course, when I've stopped doing these live streams, you can email me at hello@physicsonline.com. I do read all the kind of messages that come to me. I try and reply to as many as I possibly can. So G, great work. I hope that, or G Dominators official, I hope that you get a lot out of that. And I think the level of the training for the IFA there is going to be extreme, and that will make everything else you do seem pretty straightforward. So yeah, great work. Right. So this one here, complete the path of that a ray of laser light would take as it's reflected by these plane mirrors. So for this, you just need to remember that the angle of incidence is equal to the angle of reflection. Now, when you do a question like this, the things you need include a ruler, a pencil, and a protractor. Everybody get your protractor. You need it for maths, and you need it for the next physics paper. If you don't use it, it doesn't matter. Okay? So if you have a protractor and you don't use it, it doesn't matter. But get yourself, if you can, a lovely, nice new one so you can actually read the numbers on it. I would say at this point over here, what you want to do is mark out at 90 degrees where that kind of crosshair is here. So if I just zoom in, you want that crosshair to be exactly where that ray of light hits the mirror. We're going to do a mark at 90, and then what we need to do is just very carefully draw in our normal line. It doesn't necessarily have to be a dotted line, okay? And once you've got that, you can then use your protractor to measure the angle of incidence, and here the angle of incidence is about 45 degrees. Okay, so this angle of incidence here is 45 degrees, and that means the angle of refraction, again measured with your protractor, is equal to 45 degrees, which is down here. Okay, so then what you can do is you can draw in your reflected ray of light. Okay, and I would say that definitely do this in pencil first of all. And if you've done it in pencil, that means you need to maybe go over it in like your pen once you've actually kind of done these kind of construction lines. We do the same thing over here. So what you should do is draw in your angle of refraction. Sorry, your normal line that comes up to here. Okay, in about a minute's time, we're going to open some Lego, people, if you want to. So there will be some Lego being opened. So we'll get that open in a minute's time because it's kind of just before 8, just before the A-level stream. I would say here that my angle of incidence is about 61. And that means my angle of refraction has to, sorry, angle of reflection has to be 61 as well. And this kind of goes just down here. Okay, So basically, we've drawn that in pencil. I then recommend, once you know that's definitely correct, and trying to use a biro or a pen that doesn't kind of smudge, we're just going to go over the top so that if it's scanned in, it's very clear. I'm going to do my arrows to show the direction of those rays of light. And I'm just holding this one upside down just so it doesn't smudge. Just like that. Okay, so that's all that happens. This one here, you don't need to worry about it. It doesn't even hit that. But all of you, please, for God's sake, just take your protractor to the next exam. Okay, yeah. So I would say that definitely use a pencil. They should be able to scan it, but make sure that the pencil line you draw is big enough. Okay, right. I know, of course, lots of GCSE kids are doing their maths tonight, or they're just not revising. But for all of you A-level people, you should remember that, or you should see that on YouTube last week I did 3 live streams. Unfortunately, I couldn't do one for every single exam board. I'd love to do more for OCRB, for CIE, for international people, for everybody. But in the end, I did Edexcel. We had like a technical issue, so that kind of comes in 2 parts. OCRA and then AQA. Most of it was okay. There's a few bits where my explanations were a bit more sketchy just because I'd spent so long talking. But of course, if there's anything you need more help with, I do have full explainer videos over at A-Level Physics Online for that. Okay, right. Should we open a bit of Lego? If you want me to open some Lego, just put Lego in the comments. Something I've been doing for the streams is kind of collecting these space people. I think actually the series is going pretty well. So we've got like one of most of the people. Okay, Lego, says Josh, says the birds. Ewan, Ultraman, Bramble, scripted ones. Yeah, let's see the Lego, says Light Argent, Nee K, Olivia. Right, so this one over here. So we've got these ones so far. I think that's like all of the ones. My favourite is definitely the space person in like that suit, and also this person here because of like what they're wearing. So let's see. Okay, that is a new one. We have, is it a new one? There's one purple figure here. Let's zoom in and see what we get. Okay, this one is a different Lego figure. Again, we've got the special sparkly moon base. If you want to donate, by the way, to help me buy more Lego, I've got big plans. I think this is actually probably the first Lego I've got that's got like a transparent body. Actually, that's quite cool because if you look at the body, or the arms, they look at that. You've got like spacey arms with like stars on. I do like that. Okay, and we've got like a spacey head. There's a bit of a face there. We've got like a cool kind of like, that's quite nice. It's kind of transparent afro kind of hair there. That is awesome. They've got a club, and of course they've got a shield, which actually has, is that Orion's belt? Oh, look at this. So space person has, is that Orion, is it? Oh mate, is that supposed to be Orion? That is pretty cool, isn't it? Ripped abs. They've got like a nice kind of constellation on their shield. Hopefully that you can see that in the light. Is this kind of supposed to be Orion in the night sky or something? That is pretty awesome. Okay, right, so there we go. Look at that. Okay, right. Enough of this stuff. Let's see which ones we've got. So far, I think, in terms of the space people, we've got this one, this one, this one. We've got everything on the top row. We haven't got this one and haven't got this one, but we've got these 2, and we've got these 4 along the bottom. So yeah, I do actually quite like that. Okay, right. This is like the astrophysics one. So we do have, for everybody who's watching, 2 more sets of Lego to open in future streams. I'll probably do some of those tomorrow. I've got to say that I'm sorry that I haven't done enough astro videos, because although I think that the astrophysics is definitely some of the most interesting and exciting stuff, a lot of it doesn't come up. I mean, the amount of astro that happens at GCSE is pretty much non-existent. And even at A-level, unless you're doing like an optional topic for AQA, even for Edexcel and OCR, there's not a huge amount in there. Okay, right, tonight, this is my plan. We're going to do some questions. Now, I'm going to say it many times, but the reason I'm showing these questions from OCR is because I can't really show AQA questions or ones for Edexcel, because there have been copyright strikes in the past. So these questions, I know they are aimed at OCR exploring physics, so the OCR people in the chat, you will get a lot out of this. I'm sure you've seen these beforehand, but I just thought I'd show you my kind of exam technique for these kind of questions. For AQA, for Edexcel, for other people doing like maybe OCRB, a lot of the content is going to be the same. Okay, so the first one, again, not exactly the same, but of course, I think this is still good revision for everybody. Yeah, okay. Yeah, sometimes Edexcel have striked, and it's not Edexcel in the UK, because by the way, the people who work at AQA in the science department, brilliant, lovely people. I've done work for Edexcel this year, so I've actually been a trainer for Edexcel Pearson, delivering some content this year. And Edexcel are an amazing exam board, really friendly people, really on with stuff. But they're owned by, like, I guess, Pearson's this big American company, and all it takes is somebody working at like Pearson headquarters who doesn't understand about like the kind of stuff that's going on. They're like a big education company, Pearson. Occasionally they've done copyright strikes on people. So that's why I'm not showing the Edexcel stuff on YouTube either. So I must admit, I've not actually worked through these questions. So if you're there, please let me know in the chat what you think the answer should be. Is it A, B, C or D? I think OCR, they're totally fine with it at the moment. And I think... again, this is all completely free to view, so it's not behind a paywall, so they seem pretty happy with it. So yeah, let's just keep going with it. Right, so here we go. We've got a resistor is made from a length of wire, which gives the correct charge carriers in the resistor and the electrolyte. So in the resistor, you must have electrons which are moving because we've got a fixed metal lattice. So the protons aren't moving and the ions aren't moving. They're kind of fixed in position. So it must be either A or B. So it's a 50-50 chance. What is the charge carrier in the electrolyte? Well, it's either going to be ions or electrons. Okay, because it can't, but you know, the answers down here don't really matter. Okay, so what transfers a charge or what carries a charge in that electrolyte? The answer is ions. It doesn't say exactly what it is, but there might be like OH minus, H plus, there might be Na plus, Cl minus. All of you have done chemistry more recently than me, so it's not that one. So I would say by process of elimination, the first one is B. So great work to Josh, to Olivia, to Bramble, to Jack, getting the answer at B. Right, the next one. The half-life of fluorine 18, which is one of the... you basically need to know about technetium-99m, which is a gamma emitter. And also fluorine 18 is a beta emitter, beta plus emitter, so it's used in positron emission tomography. So for this, if you're not sure, draw a graph. So here we go. We've got this. So at a time of 4 half-lives, we've got 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Okay, so basically T is equal to 4T, so it's basically down here. Now let's imagine we started at N0 and now we have N. We've basically gone through 4 half-lives, so it's basically halved, quartered, eighth and 16th. So basically it's 1 over 2 to the 4. So it's basically a 16th of the original amount. Okay, so whatever N0 is, it's going to be equal to 16 times N. So whatever this value of N is, N0 must be 16. Okay, so how many fluorine 18 nuclei have decayed in the time interval from T equals 0 to T equals 4? So effectively, if that there is equal to 1N, then this height up here must be equal to 15N, because the total height is going to be equal to 16N. That's kind of my visual way of doing it. So I would say that it's 16 minus 1, which is 15. So the answer, I think, is C. Okay, Mathilde, yeah, is this A-level? I'm on Lobo. Yes, this is A-level. So yeah, the answer is 15. So how many fluorine? It's going to be, even though it's the 16th of the original amount, if we've got 1N left, there were 16N initially, then we must have had 15N that have decayed. And I think sometimes you can do it like mathematically, or you can do it kind of like graphically. Whatever helps you, nobody cares as long as you get the right answer. So that one over there, the answer for 2 is C. Okay, you do need your calculators here. because I haven't actually worked this out yet. So the activity of an alpha emitting source is 120 kilobecquerels. The kinetic energy of each alpha particle is 4 mega electron volts. What is the rate of energy released by the source? So this is the energy of each alpha particle. So the energy of an alpha is equal to 4 mega electron volts. But if it's emitting 120 kilobecquerels, that means it's going to be 120 times 10 to the 3 particles being emitted per second, each of which have an energy of 4.0 times 10 to the 6 electron volts. Okay, so we could do an intermediate calculation and just work out the energy. So that's basically a total of 4.8 times 10 to the 11 electron volts per second. We can, of course, convert that from electron volts into joules by dividing by 1.6 times 10 to the minus 19, which is then equal, by multiplying which is equal to 7.68 times 10 to the minus 8 joules per second. And of course, a joule per second is just a watt. So I would say, looking at this, the answer tends to be C. So for this one, I didn't look at the answers. And I basically did the maths in the way that I thought was appropriate. And again, I have not seen these questions. I'm doing these blind, so fingers crossed I kind of get them right. I didn't look at the answers. I just went straight for the calculation, and that allowed me to get this. So the answer is C. I would say to Mitchell, is it worth writing out working for yourself and multiple choice questions? Yes, it is, even though it's only for yourself. I mean, this isn't a fully formed equation. It's like I've just noted down the energy for each alpha, then I've just taken the activity times the energy per particle to get the total energy in electron volts, and then I didn't even sort of say how I went from electron volts to joules, but I would say write it out yourself. Okay. Which of the following statements correctly describe radioactive decay? Radioactive decay can be modelled using dice. Of course it can. I think that's even a specification point in OCR. So you can throw dice, you can look at the number that kind of land with a certain number up, you can take those away, and you can basically model this exponential decay. The radioactive decay of nuclei is random. Yes, it is. Completely random. And also spontaneous. That means there's nothing you can do to influence it. You can't heat it up, cool it down. It is a spontaneous, random decay, and you can model it using these. So if 1, 2, and 3 are correct, then D must be the correct answer. And by the way, Albie, Josh, Jack, Mitchell, Bramble, Pumu, Penguin, excellent name, all of you correct. Right, a gamma ray photon. Okay, this one here again is another calculation. So a gamma ray photon of frequency creates a particle-antiparticle pair. The particle-antiparticle pair have 0 kinetic energy. What is the mass of the particle? So here I would be saying that the energy is equal to, or the delta energy is equal to the change in mass times c squared. Okay, and of course the energy is going to be equal to hf. Okay, so we've got 6.63 times 10 to the minus 34. Again, don't forget you will have your data books. This is just one of the things I've got on my website. But if you need to check anything, you know the value of that, but it's 6.63 times 10 to the minus 34. Yes, I put the right number down. Do check your constants, because when you're stressed, then things do get a bit stressful. So we've got the value of Planck's constant. We're going to multiply that by the frequency, which is 6.76 times 10 to the 22, and that's going to be equal to mc squared. So if we divide that by the speed of light squared, which is 9 times 10 to the 16, so just 3 times 10 to the 8 squared, this will give us our change in mass. Okay, so that's 6.63 10 to the minus 34 times 6. So the mass is equal to 4.9799 times 10 to the minus 28. But of course that's the mass equal to the particle-antiparticle pair. So the mass of the particle, so that's basically 2 times the mass of the particle. So the mass of the particle is going to be equal to half this, which is 2.5 times 10 to the minus 28, or 2.49 times 10 to the minus 28. So again, without looking at the numbers, the answer is A. I suspect lots of people will have worked out the change in mass, but because what we have is basically a photon comes in and then it creates 2 particles. Okay, I suppose the photon comes in and it kind of creates 2 particles like this to kind of conserve momentum. No, it basically creates 2 particles. They have 0 kinetic energy, so they're not really moving, but basically this photon, the energy of that photon makes 2 particles, and therefore the total mass of these is equal to the change in mass, and therefore the mass of one particle is going to be half of that. Okay, right, and it's a particle-antiparticle pair. Right, that all good? Everybody all right? Okay, let's do another one. Potential divider circuits. Brilliant. I think if you're doing AQA, then you probably won't have many questions on electricity, so this is all behind you. So let's have a look at what the answer could be. So we've got a potential divider circuit, 9 volt supply. At room temperature, the PD across a thermistor is 4.5. So at room temperature, that's 4.5, and that's 4.5. Okay. The temperature of the thermistor is increased, and the resistance decreases by 20% from its previous value. So I'm going to say that at room temperature, we've got an equal share of that 9 volts. So let's say that the thermistor has a resistance of 4.5, or just the thermistor has got a resistance of R, and the resistor has a resistance of R. Okay, now at a hot temperature, this is my approach, at a hot temperature, that's got a resistance of R, and this decreases by 20%, so that's 0.8 R. Okay, now that means the total resistance, RT, is going to be equal to 1.8 R, and the share of the potential difference of this is going to be equal to 0.8 over 1.8 times 9.0. Okay, because we know that like R1 over R2 is equal to V1 over V2. Okay, so we know that the ratio of their resistances is going to be the same as the ratio of the potential differences across each of them. So 0.8 divided by 1.8 times 9 is equal to 4. So here I think 4 is the answer. So the answer for 6 is B. What have people said? People are very quiet on this one. People not liking this. So what I've basically said is we've got the resistance of the thermistor is R, because that's the same as the value of the resistance of the resistor when this is set up at room temperature. When we go to a hotter temperature, the resistance of that thermistor goes down to 20% of what it was, so 20% off, so it's 0.8 R, and you've got the same value of that fixed resistor. So now the ratio of this resistance to the total resistance is going to be 0.8 over 1.8, and if we multiply that by the PD across everything, that will tell us the PD across this. So now that would have 4 volts across it, and that would have 5 volts. Because that's got a lower resistance, that's got a higher resistance, that's what we get. Everybody hates potential divider questions. I can see everybody in the chat has gone quiet. Nobody is offering their answers there. So I do think that everybody hates potential divider circuit questions. That's just the way it is. You're going to have some AQA. I suspect you're past that now. Right, number 7. Let's see if people can do this. So, a particle is moving at right angles to a uniform magnetic field of flux density B. The particle of mass m, charge q, moves in a circular orbit of radius r. So the momentum, so we know that the force in it is going to be equal to BQV, and also that force is equal to the centripetal force, which is mv squared over r. We can equate the two things together, so I'm just going to get rid of that. We know there's a v there that cancels with that, so BQ is equal to mv over r. So mv is equal to BQR, and m times v is just momentum. So the momentum depends on B, Q and R. So I would say for this, the answer, again, without looking at the answers beforehand, is A. This is better. So Jack, Mitchell, Ibtisam, Bramble, Josh, loads of people getting the correct answer. So you might just know this, but again, if you're not sure, this one here comes up all the time. You're equating the Lorentz force due to the magnetic field on a moving charged particle in the magnetic field is equal to the centripetal force on it because it's moving in a circular path, and therefore BQ equals mv over r, mv equals bqr, so the momentum is equal to bqr. Good stuff. Right. The diagram below shows two long current carrying conductors, X and Y. I think basically this is how the amp used to be defined. I think one of the SI base units was based on like the size of the force between like parallel wires distant to 1 meter apart. So the conductors are parallel to each other. Y experiences the force because it is in the magnetic field of X. So which row gives the correct direction of the magnetic field at Y due to X and the direction of the force experienced by Y due to this field? So let's just think about X first of all. So this is the wire, and I'm going to use my right hand grasping rule to basically think if the current is going upwards, then we'd have the field lines, these kind of concentric circles that get further apart. So that's kind of like the field around it, and here the arrows would be coming out this way and then back into the paper. So I would say that the direction of the magnetic field at Y due to X is going to be going into the paper. So it's down into the plane of the paper. So it can't be up. So it's not this one. And it's not this one. Now, of course, there's also going to be a field due to Y, which is going to be in the same. So basically I need to have like two right hands. And what we see then is that one set of field lines at, so now we'd have Y at this position over here. We'd have field lines coming in this way, and from Y there would be field lines going in the opposite direction. So rather than the field lines going together, you'd have field lines in opposite directions, which kind of effectively cancels them. So I would say then that means that the field is going to be the two things are going to be kind of attracting each other, because you basically got field lines in opposite directions. So you've got like an opposite, an opposite field, and therefore it's like the north attracting the south, rather than field lines going in the same direction where they'd be repelling. So I would say the force at Y is going to be to the left, and actually the two wires kind of do move together. So here the force is to the left, and the answer for this is C. That was a tricky question, I think. So I think a lot of people might have got that incorrect, but loads of people putting the right answer in the chat. So great stuff. Okay. Right, the next question is about a simple experiment looking at refraction through a rectangular glass block surrounded by air. So which statement is correct? The angles theta and phi are the same because the glass block is surrounded by air. Actually, yeah, that must be true, because whatever that angle is must be the same as that, because this ray of light comes out and it's going to be parallel to the ray of light that sort of comes in. Okay, so that's definitely a correct statement. So I reckon 9. I would say A is going to be correct. But before I put that as an answer down, then I think I just read the others. So the product of sine theta and the refractive index of a glass is a constant. No, because sine theta times n would be equal to like n sine. So sine theta in material 1 would be different, because although n2 would stay the same, theta 2 changes, so this thing changes. So that's not correct. The refractive index of glass is less than the refractive index of air. That's not true. The refractive index of glass is bigger than the refractive index of air, and it slows down the speed of light by a big factor, so that's not true. The speed of light is the same in both glass and air. That's not true, because the glass slows down the speed of light there. So here the answer must be A. Okay, Sorry, there's some chat going on. I'm afraid if I've got time at the end, I'll maybe explain a bit more about Lenz's law. But yeah, basically, I think as Jack is saying, if you've got a magnetic ball falling through a copper pipe, as the ball is falling, it induces an EMF because you've got a moving magnetic field near a conductor. That induces an EMF in the conductor, and because you've got copper, there's effectively lots of kind of complete pathways for the electrons to move around. And then you've got electrons, this kind of eddy current that's kind of flowing in the metal. It's got a low resistance because it's got a big surface area. There's lots of ways for the electrons to move. And that means we then have, with this moving electron, we have an electric, a chain, basically you've got a charged particle moving. When you have a charged particle moving, we have an associated magnetic field. And this basically causes the copper tube to act a bit like an electromagnet. But it's a bit like the south end of the magnet falling is repelling against the south end, which is pointing up inside the tube. And basically, it's a bit like having opposite magnets, magnets with the same pole, so they're repelling. So there's a repulsive force which slows it down. Okay, and I think Ibtisam and other people are putting some really, really good answers there. So Jack as well, thank you so much. Okay. A proton of mass 1.67 times 10 to the 27 minus 27 kilograms travelling at this speed. The table shows the mass and speed of 4 particles. Which particle has the same de Broglie wavelength as the photon? So again, you will be given this, but you know that lambda equals h over mv. Okay, so which particle has the same wavelength? Well, basically, h is going to be a constant, and we want to find something where 1 over mv, because that's going to be proportional to 1 over m, or equal to 1 over mv, we basically want to have something that has the same momentum. So all I need to do is have another column where I multiply these two things together. So basically, the momentum of the proton is 1.67 times 10 to the minus 27 times 2 times 10 to the 5. So the momentum of the proton is equal to 3.34 times 10 to the minus 22. And we just want to find out by multiplying these two things together which of these numbers are the same. So 9.11 times 10 to the minus 30 times 5 times 10 to the 5 is equal to 4.55 times 10 to the minus 24, so it's not that one. The next one is 2.64 times 10 to the minus 22, so it's not that. 2.49 times 10 to the minus 28 times 2 times 10 to the 5 is 4.98, so it's not that one. And then we've got 3.34 times 10 to the minus 27 times 1 times 10 to the 5 must be 3.34 times 10 to the minus 22. So it must be this one. So the answer for 10 is D. Okay, D, says Jack, Ibtisam and Bramble. Great stuff. This one here, again, doesn't matter what your working out is. This is all doesn't make much sense to most people. So I've just written down the equation for the de Broglie wavelength. We know, of course, that if it's got the same wavelength, then h over mv is going to be a constant, so 1 over mv equals 1 over mv, and that means we just want to know the product of these two things, which is the momentum of those things. And Ben as well, getting the correct answer, D. Great stuff, Ben. Okay, right, for 11. A beam of sound of intensity I naught is reflected off the surface of water. The amplitude of the reflected sound is a quarter of the amplitude of the incident sound. So let's say the amplitude of the incident is equal to 1, then the amplitude of the reflected sound is going to be a quarter of that. What is the intensity of the reflected sound in terms of I naught? So for this one, this is something which is a little bit more specific to AQA, and for AQA you need to know that the intensity is proportional to the amplitude squared. Okay, now initially the amplitude was I naught, and that's proportional to AI squared. So let's just say that's equal to 1. The second amplitude, let's say the reflected amplitude, is going to be proportional to a quarter. squared, which is going to be 1 over 16. So reflected intensity is equal to the original intensity divided by 16. So I would say that looks to me like 11A. So I think A is the correct answer. A says Bramble. Jack says A with a question mark. This one here is more of an OCR thing specific. Basically, this is an OCR thing. You just need to know about how the intensity is related to the amplitude of that wave. I think my blue pen is running out. I've done so much writing. I think the red one I've got as well is almost dead. So I think these are on their last legs, these pens. Okay. A small sample of muscle has a volume of 1 centimetres cubed and a mass of 1.10 grams. We've got the speed. What is the acoustic impedance of the muscle? So let me just get... Right. I'm just going to get my OCR data sheet. This is one I did all on one side of A4 or A5. If we're looking at the acoustic impedance, Z is just equal to the density times the speed of the wave in that material. And density is just equal to the mass divided by the volume. So that's going to be equal to that times C. Now, I would say that the mass was equal to 1.10 times 10 to the minus 3. We're going to divide that by the volume, which is 1.0 times 10 to the minus 6 cubic meters, times that by 1600, and that will then give us an answer equal to 176 times 10 to the, let me see, 10 to the 6. So I reckon this is equal to this answer over here, and therefore 12, the answer is C. I think that's correct. So this one here is OCR only, I think. So this is OCR only. Don't worry if you're AQA and you're not doing the medical thing. But this question here is using a simple equation they give you in the data sheet. It's a simple about link between mass, volume and density, but it's more about can you convert from centimetres cubed and grams into an appropriate SI unit to actually do the rest of the calculation. Yeah, so you just copy the units to work it out. Yeah, that's all it is really. Okay. Which expression is correct for the binding energy of a hydrogen-3 nucleus? So basically, hydrogen-3 has got 1 proton and 2 neutrons in it. Now, the mass... So, okay, what's the binding energy? The binding energy is equal to mc squared. Okay, so the binding energy is going to be equal to the mass, which is equal to the mass of the proton plus the 2 times the mass of a neutron, which is basically the things we add together, and then we take away the mass of the nucleus, m, and we multiply all of that by the speed of light squared. Okay, so that's going to be our mass defect. So this thing down here is equal to the change in mass of that nucleus. So we've added a proton to 2 neutrons, and therefore this one over here, it's got the same thing in a different order. I reckon D is the correct answer for 13. There we go. D, says everybody. Scarface, you're not finished yet. You might be finished tomorrow, but at the moment there is still hope. Don't give up hope just yet. Yeah, Bramble, Ibtisam, Josh, Ben, Jack, Argon, hello Argon, Joshua. Yeah, all of you getting the right answer of D. You're doing good, people. You're doing good. I know I've gone slightly beyond the time. We've just got 2 more questions left. A wire in a circuit obeys Ohm's law. Now, of course, Ohm's law basically says that the potential difference across it is going to be proportional to the current, provided T is constant. So, the current in the wire is directly proportional to PD across it. Yeah, that's true. And that's basically what it says up here. The current in the wire is inversely proportional to its resistance. That might be true, but it's not about Ohm's law. The resistance of the wire is directly proportional to its length. That is a true statement, but it's not about Ohm's law. and the resistance of the wire is inversely proportional to its cross-sectional area. Again, that's a true statement, not about Ohm's law. So I think for 14 the answer is A. Temperature is, how can temperature be constant if current is increasing? Scarface, what we're saying is that we have a constant. What we can say is that if you have a current only moving for a short amount of time, then the heating effect won't change the resistance of that. So we're saying that basically, you know, imagine that a current fluid. Imagine the current went on for a time equal to maybe 0.01 of a millisecond. Okay, when that's the time, and the current might be like 3.0 amps, then the potential difference might well be, you know, say 6.0 volts. Okay, now that's probably enough time that the heating effect is negligible, but you could do that multiple times at different currents, and you'd find that these two things are still directly proportional. So you might do it again at 1 amp, and then you might find that this is equal to 2.0 volts. And as you do this many times, even for a very short amount of time, we're just looking at this and how that relates to that for a very small amount of time, and therefore the temperature is constant. Okay, an electron has both charge and mass. The electron has a gravitational field and an electric field around it. So here's the electron. Okay, now there's going to be around it an electric field which shows the direction that a positive particle would move. So we have field lines coming into the electron like this. Okay, so that's going to be my electric field, and of course you could have maybe 8 lines. If we then had lines to show the gravitational force, that's also going to be into it like this. So maybe this is the gravitational field, so that's G. So that one there is correct. Both patterns show parallel field lines around the electron. I don't think that's true because you've got a radial field and therefore the lines aren't parallel. You only get parallel lines in a uniform field, which may be between plates or something. That's true. They both obey an inverse square law. They're both proportional to 1 over r squared for both the gravitational field and also for the electric field. So this one here is true. The direction of both fields is the same at any point around the electron. Well, that must be true because that's true. So the field lines must always be pointing towards it. So that's true. So the one that isn't correct is B. There we go. Yeah, so there we go. Those were some questions. Hopefully that helped some people. I know if you've been doing OCR, you might have seen these questions already. But if not, then it's always good to kind of go over them again. And do not write on this page. So basically that is the end of the live stream tonight. That was the 2022 paper. My plan for anybody who wants to come back tomorrow night and the next night and the next night is tomorrow I'm going to do 2021. I'm going to use an OCR paper because again I think the questions are pretty good. Even if you're an AQA, OCRB, EdXL student, the questions are useful for anybody doing OCR as a recap as well. I'll be doing 2021 tomorrow night. I'll be doing 2020 on Tuesday, and I'll be doing 2019 and probably 2018 the night before the exam when everybody starts panicking. If you want to find any more information, of course, I did live streams last week for EdXL, OCR and AQA. They're about 3 hours long, but you can skip forward to the bit you need. Of course, if you want to, you can then find even more videos over at alevelphysicsonline.com. If you want to have free access to that, ask your teachers to sign up for a school subscription. That allows me to keep doing what I'm doing, keep being in this studio, and also make the new studio, which is coming together quite soon. So yeah, thank you everybody. Thank you, Ross. Should I have wine? I don't know. I was trying to not drink. I'm doing like a marathon next weekend, but it's like an off-road one and it's like 26 miles. So I probably shouldn't be drinking. I should just be not drinking. But anyway, who knows? So yeah. Somebody's out. Okay, I shall answer some questions for a couple of minutes. Somebody's out of AQA papers. What should you use? I would say OCRA is pretty good, or EdXL. But just make sure you do questions by topic if you can. Like PMT have got some good ones, like question packs by topic, and that means you can just focus on the things that you need. Eddy currents, Ibtisam. I did this the other day, but basically, if you've got maybe some metal and you've got a change in magnetic field near it, so maybe we've got a big coil of wire kind of looped around it like this or something. Okay, when you have a changing direction of current here, we're going to have an associated magnetic field kind of in the centre of that coil, which is going to cause a magnetic field here. And of course, every time you have a magnetic field, this then causes electrons to move, and then that means we have an electric field. And of course, electric fields go and make magnetic fields and kind of back and forth. So every time you have a magnetic field here, it's going to cause the electrons in here to move around. Now, because you've got something which is massive, effectively, we know that, of course, the resistance is proportional to 1 over the area. If you've got a bigger area of wire, we're going to have a smaller resistance. Here, the area is massive, so the resistance is really small. And that means we can have very, very large currents of electrons moving around. And they're not constrained within the wire. They can just move anywhere within this material. And that's what we call an eddy current. Now, of course, with an eddy current, you're going to have a very large current, and that's going to lead to a large heating effect, because as you have a bigger current, we call the heating effect, so the temperature goes up. And the way that we reduce that is we basically, rather than having a big block of metal, is you kind of laminate it like this, and then you have an insulator between the layers of metal. And that means that the electrons, rather than being able to sort of just go up and down, they can only go up and down a small amount. So it reduces the size of the currents. And of course, you can then take that stage further. You can have basically like a metal powder within like a resin of some kind. You can kind of laminate it basically in 2 or 3 dimensions, not just in one plane. And if you have something like this, it really reduces the size of the current, because everything's constrained within these small little domains here. And so by laminating something, we reduce the effect of the eddy currents, and that means we have less heating effect, and we make transformers more efficient. Hopefully that helps, and that is the end of the live stream. See you all tomorrow.